Morning, and I'm going to introduce my paper on the subject of the computer science, engineering, and information technology. My name is Fuyao Ling, and it is my great pleasure to present our research titled BridgeGap, a smart behavioral profiling and matchmaking system for bridge players using the real-time gameplay analytics, co-developed with Andrew Park. This project is an attempt to introduce adaptive technology to the intellectual sport of bridge, targeting one of its long-standing challenges, partner and teammate matching. Over the next 30 minutes, I will guide you through the technical structure, experimental results, and the broader implications about this mobile-based system. Bridge is globally recognized intellectual sports that relies heavily on partnership and strategic communication between players, despite its rich tradition and intellectual complexity. One of the main challenges faced by the bridge community, especially young or novice players, is the difficulty of finding the right partner or teams to practice with or play with. So in today's digital-first environment, much of the social interaction and environment has moved online. In some areas, the traditional face-to-face bridge clubs are dwindling, and the few online bridge clubs that exist requires users to have their own partner, making them less friendly to the individual interests. And random matching of partners fails to take into account differences in skill level, preferred playing styles, and the need for the social contact. This afraid many interesting players, especially the beginners or the casual participants, leading to a decline in global bridge participation. According to American Contrast Bridge League, bridge membership has been declining steadily in recent years, with many players citing the difficulty of finding a partner as the main reason for the decline in participation. Furthermore, existing platforms for matching bridge partners often rely on static data or pre-arranged teams. This creates a disconnect in games that depends so heavily on mutual understanding, cooperation, and adaptive strategy. As a result, we believe that bridging the gap between the intelligent matchmaking and real-time behavioral compatibility is essential to not only preserving the game but evolving it into the digital age. S I will introduce the project overview to you first. The BridgeGap is a mobile platform designed to connect bridge players based on real-time behavioral insights. The project addresses the challenge of the partner matching and community building in modern bridge by utilizing the in-game data, such as the bidding and the game history, collaboration scores in the MP score, and player performance. The system includes three major components: matchmaking, gameplay, section and management, and a visual profile with radar chart analytics. Firebase services are used for user authentication, live data updates, and stat storage. BridgeGap is designed to match players based on skill level, play style, and user preferences, while also offering features such as performance tracking, chat, data visualization to help players grow and connect through gameplay. This integration makes BridgeGap not only a tool for matchmaking, but also a platform for learning and social engagement. It enables data-driven personalization without relying on self-reported player traits, and instead constructs dynamic profiles directly on interaction history. About the technical architecture. The BridgeGap applications is structured around three major components: matchmaking, gameplay, and user profiles. These components work together to provide an integrated experience for users to connect, compete, and improve their skills in the game of bridge. This application is built using Flutter for cross-platform development and Firebase, of course, Supabase in certain area for back-end service, including the authentication, real-time data handling, and the cloud storage. These components provide a cohesive experience that connects player, facilitates gameplay, and promotes skill development in the global bridge community. BridgeGap's core functionality revolves around a dynamic matchmaking algorithm powered by Firebase real-time database and users' profile data. Users can set preferences such as game type, availability, and skill behavior. The real-time database ensures that in-game state updates, such as the bids and the score changes, are immediately updated to all clients, while Firestore keeps long-term player metrics organized and synchronized. About the matchmaking engine, BridgeGap's matchmaking engine is responsible for connecting users based on their skill level, their bridge playing style, and availability. It uses the Firebase file store to store each user's historical data from when they played and applies the data to quantify the user's bridge level, as well as their preferences, like showed here, which are not stored in each user's personal profile. When a user makes a partner match, the component adjusts weights of different data based on the custom logic, the preferences for bidding ability, the declaring ability, or defensive ability, calculating the quantified historical data of the remaining users to look up in order to form a balanced preference consonant match. The design directly supports BridgeGap's pairing algorithm, which uses the stored performance history and preferences to calculate the compatibility scores when forming balanced matches. By preparing a clean and consistent player dataset during the system initialization, the matchmaking engine has reliable input to work with, laying the foundation for the meaningful and the preference, the driven partner connection. The compatibility score is calculated dynamically each time a search is initiated. Player preferences can be adjusted explicitly or inferred implicitly from repeated decision and game outcomes. These interactions are reflected as updates to a player's profile, making the matchmaking adapt to their actual habits over time. About the gameplay control. The game component manages bridge gameplay, including the choice of game rooms that can be selected, the choice of player seating, and the bidding, dealing, rounds, scoring, and synchronization between players once they are in the game. The front-end logic uses Flutter and the real-time updates using a Firebase real-time database. This component requires careful section control. User interface state management and consistent data flow to ensure that all players run the game in the same and proper manners with the rules of bridge. The start game section function is responsible for initializing the bridge game after a match is created. First, the create room method initializes the game room in the Firebase real-time database and defines the readiness of the player's seat. Once a room is created, it references the state of the game in the Firebase real-time database. The system then generates a specific or random distribution of cards, manages the player hands, records all the bidding action, and calculates scores, which are synchronized across the users in real time. Game state management includes monitoring the betting sequences for legality, controlling player turn taking, and calculating final results according to contract fulfillment and defense. The session remains active until all four players complete their boards or destination is handled. At the end of the session, player profiles are updated with extracted metrics from the session. About the player profiling and the visualization. The profile component visualizes player performance using a radar chart, displaying metrics such as bidding skill, the defense, the activation, and bridge morality. These values are stored in Firebase and updated after each match. This component helps users track their growth and informs the matchmaking system by offering a more detailed view of the player's strengths and playstyle. These updates enable dynamic and personalized user profiles in the application, which may be used for features such as matchmaking, the profile display, or tailored user experiences. The radar chart system provides users with a clear graphical like interpretation of their evolution, such as players over time. Each dimension in the chart reflects average performance across multiple sessions, providing both absolute and relative indicators of player behavior. When the player reaches significant milestone or diverges from past behavior, the system updates the shape of their charts accordingly. And now I'll talk about the two experiments. The first experiment, the behavior preference inference. To investigate player preferences, gameplay data from 20 bridge boards per user was collected and stored using Firebase. Each user's actions, such as the bid frequency, the risk-taking behavior, the completion rates, and the collaboration were recorded and labeled. Player was then classified using the statistical scoring range. For example, a player with frequent higher baits and fast turns may be categorized as a aggressive competitive. The average cooperation score between the competitive player and the casual player at a similar rate was 71, 5 points higher than the score between the two casual players. The lowest cooperation score was 40, and the highest reached 87. The results showed at a 87% accuracy rate in preference inference. These findings validate the radar chart systems for performance visualization and confirm that the app's analytics engine can provide meaningful profile insights. The user's clustering also allowed us to identify players with strong defensive capabilities who would not be matched under the traditional statics filters. Now we'll talk about the second experiments. the competitive engagement. To test competitive engagement, we created eight test accounts representing different user types. Each account participated in an 8-board bridge competition. Using the app's match mode, we recorded metrics such as match points, the MP scores, the quit rate, and performance consistency. The results showed that the competitive players had the highest MP scores, the average of 64, and the lowest dropout rates, like 0, while newer players had a higher rate of incomplete matches, about 37.5%, and the lower average score, the average is 22. The time per board was also longer for casual players. The average is 701 seconds, while the competitive players averaged around 425 seconds. This experiment revealed that competitive users were more engaged and consistent, indicating that the competitive modes appeal to this group. However, less experienced players struggle to complete all boards, suggesting that the onboarding or assistant gameplay might be needed. The difference in time per board also illustrates the need for pacing-based matchmaking, where users can be grouped not only by skill but by game rhythm. This insight supports the future system refinement to accommodate cognitive pacing styles. About the comparative studies. The studies by solving introduces a framework identifying the 5 intermediate level traits through a 66-item survey about 1,300 bridge players. In contrast, BridgeGap employs a real-time behavioral data from gameplay, such as the bidding frequency and the collaboration scores, to infer players' preferences and enhance matchmaking, while the previous studies rely on self-reported data to understand the player psychology. BridgeGap's approach focuses on the observable in-game actions to personalize user experiences. Similarly, this study by Bellier and Searing used intelligence theory to analyze player traits, while Hanherbst emphasized the cognitive motivation through the interviews. BridgeGap, in comparison, uses the direct game telemetry, eliminating self-reporting biases and improving their skills. About the implementation challenges, one key challenge is managing the real-time user data and multiplayer interactions through Firebase. Potential issues include the latency during the real-time matchmaking or data inconsistency across the multiple services. Another challenge is designing a rating algorithm that accurately reflects the player's ability over time. Ensuring that the bridge game functions correctly across the multiple sections and devices involves consistent the state synchronization and turn control. Authentication must also be reliable, so integrating the Firebase auth with proper section handling and the security roles is necessary to protect the user data and maintain stability. A major concern is designing a rating algorithm that accurately reflects the player ability over time and adapts based on real match data. Furthermore, avoiding pairing loops, handling inactive users, and allowing players to report the uncooperative partners are important usability requirements that the current systems partially supports. About the limitations. BridgeGap's current matchmaking system is primarily based on the static analyze and the simple preference filters, which may not capture the full differences of the player compatibility. Some behavioral metrics, such as the collaboration score or bridge morality, are still subjective and require a more robust tracking mechanism. New players may also have the incomplete data, making the early matchmaking less reliable. Another limitation is the lack of the machine learning implementation to dynamically adjust the player's models over time. These limitations are anticipated during the early development phase and noted as areas for the future improvements. In particular, we acknowledge the current absence of players' verification methods, the comprehensive anti-cheating controls, and the cross-platform compatibility extensions, which would be required in scaled deployment. About future work, giving more time and resources, we would implement a supervised learning model that continuously refines the player categories based on the updated match performance. We would also expand the testing to a larger and more diverse user base to validate the consistency across the skill levels, the regions, the gameplay styles. Lastly, we aim to improve the user experience through the better UI for stats visualization and guided the learning features for beginners. In addition to these plans, we also seek to design adaptive tutorials that respond to the user's real performance trends, helping to close the gap for new and disengaged players. We also aim to develop a feedback module to collect the user satisfaction rates after games, using the results to refine the matchmaking compatibility beyond the raw skill alignment. These are the references of the paper. In conclusion, BridgeGap successfully addresses the challenge of connecting bridge players through intelligent, data-driven matchmaking and profile analysis by using the gameplay behavior instead of survey. It offers a scalable and engaging way to build community, improve the skills, and personalize the user experience, making Bridge more accessible and enjoyable for all players. BridgeGap proves to be a powerful step towards a smarter, more connected Bridge community. Okay, that's all. Thank you for your attention. I welcome your questions and feedback.